Let's do a little review on chapter 9 for exam 7. And I'm anticipating doing part 1 today and then finishing up on Tuesday. At least that's the way the schedule is set up, so we don't have to rush. All right, this is chapter 2, and as usual, I've got several. Let me decrease that, get more of it in there. There we go. Number 1. Which of the following molecules contains a central atom with sp2 hybridization? Remember what's required for hybridization. If we have groups here, we have 4, 3, 2, 1 in groups, then the geometry and the electronic geometry actually is tetrahedral. This is trigonal planar. This is linear, and this doesn't make any sense. Then let's go ahead. With 5 groups, we have trigonal bipyramid, and 6 we have octahedral. That's what we work from the VSEPR. Okay, so if we need to hybridize, we count up the required number of groups, and we start with the S's and the P's. So if we need 4, we need the S that we have, and we need all 3 of the P's, because there are 3 orbitals in the P subshell. Trigonal planar, we only need 3, so there's sp2. Linear, we only need sp. And what that does is this one, it leaves an unused P available for something else, usually a double bond. And this one leaves 2 p orbitals, which could be a triple bond or 2 double bonds. And then trigonal bipyramid, we can only have 4 from the S and the 3 P's, so we have to add a D to get the 5 groups. And octahedral, we add 2 Ds. So that's the pattern. That makes it easy to answer this question. Which one has sp2 hybridization? sp2 is trigonal planar, which means 3 groups around the central atom. So if we look at A, each one of those atoms, aluminum and phosphorus, they have 4 groups around them, so A can't work. Boron trifluoride works perfectly. It's got 3 groups around the central atom boron. So B is the preferred answer. The others don't work. C doesn't work because it has 4 groups. It has 3 atoms, but it has a lone pair. And also for the hydrazine, the N2H4 of D, you've got 4 groups with a lone pair making up the difference on each of those nitrogens. And then the beryllium dichloride has only 2 groups, so it has to be linear and sp hybridized. All right, so we got that one out of the way. Let's take a look at number 3. Good. All right, consider the molecule of the following hybridization choices. What is the hybridization of the carbon atom that is double bonded to oxygen? Okay, so we have these 3 carbons, 4 carbons. I think we have a nitrogen there, we have chlorine here, hydrogen there, and we have a, is that right? Nope, put it on the wrong one. It has to be here, right? Yep. This one has the double bond oxygen. That's known as a carbonyl group. And these are hydrogens. So let's see, octet, 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 octet. Yeah. They probably left that out, yeah. We're interested in this one right here. So the hybridization here would be 1, 2, 3 groups would be sp2. Okay. And while we're here, this one would be sp3. This one would be, let me see. We left out the lone pairs. That must be a lone pair there, right? No, there's a hydrogen, sorry. So this is also sp3 for the carbons. This carbon is sp, and this nitrogen is also sp. Because it only has 2 groups around it. This one has 2. This one has 4, 3, 4. So you could do any one of those. Okay. How about number 5? Consider this molecule. 1, 2, 3, 4, 5 carbons. We have hydrogens here, nitrogen there. We have a carbonyl here. And we have a hydrogen here and 2 hydrogens here. Now it drew them in shorthand version, but that's what it should look like with a double bond there. Okay. So the reason I drew it that way is because it's easier to answer the question if we see it this way. If you see it the way it's written there, you have to understand that this is written like that. Or sometimes it's written like this. But then when the next carbon comes along, it only has 1 hydrogen. And in organic chemistry, when you have a string of carbons and hydrogens in there, the hydrogens are always identified with this carbon or that carbon, and the carbons are attached to each other. So if it doesn't put the double bond in there, you know, carbons have 4 bonds somehow. Like this 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. That's characteristic of carbons. So that's the reason I wrote it this way. So it's easier to detect. So the hybridization here is sp2 here because there are 3. We have 1, 2, 3 here, it's sp2. 1, 2, 3 there, sp2, sp3, and sp. So it's 2, 2, 2, 3, 1. 2, 2, 2, 3, 1 is A. Okay. Number 6. The hybridization of selenium and SEF6. Okay. In order to start from a formula like that, you got to draw the Lewis structure. So selenium is in the same group as oxygen. That means it has 6 electrons. And 6 times 7 for the fluorine is 42. That means 48 electrons. So we put selenium in the middle, and we have 6 fluorines. Okay. 2, 4, 6, 8, 10, 12. Means 36 electrons left over. If we put 6 around each one of these fluorines times 6, that's 36. And for all of our electrons. Now we've got 1, 2, 3, 4, 5, 6 groups, which means D2sp3. It is octahedral. Let's see. Do I want to do, did we do that one somewhere else? Number 8. I don't have 8 marked, but I wonder if it shows up someplace else. Yeah, it does, but we didn't do it for that one. I think we ought to do it. Simply because it's kind of odd. Yeah, let's go back. Here we go. Let's do 8. Because it can be confusing. When we have this skeletal structure, we have 2 carbons here, then we have a carbon each here, 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 and then a nitrogen. That's the skeleton. Tetracycloethylene has the skeleton shown below for its Lewis structure. How many of the atoms are sp hybridized? Okay, what we have to assume is that the way the problem is stated, there are no other atoms in there. We don't have to put hydrogens in, nothing. So what we would do is add up all the electrons and complete the Lewis structure for this. We have 1, 2, 3, 4, 5, 6 carbons. So that's 6 times 4. Yes, 4 equals 24. And then nitrogens, 1, 2, 3, 4 times 5. Oops. 4 times 5 is 20, right? We have 48 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. That means we have 30 left, 30 electrons. Okay, if we put 6 more to make an octet around each nitrogen, that's 4 times 6 is 24. 6 electrons left over. Okay, where do they go? Our inclination is to put them on these carbons. Right, we go 1, 2, 3, 4, 5, 6. That seems kind of lopsided, doesn't it? Let me make sure I counted it up right. 6 times 4 is 24. 4 times 5, yes, it's 20. Oops. Didn't I make a mistake? $26. And then 24. That means only 2 electrons. Okay. It's good to keep an eye on yourself. Okay. Where would be the best place for those 2 electrons? Well, if we put the 2 electrons, let's see, we've got 2, 4, 6 around these carbons. 2 electrons in there on one of those give us an octet, and then we could make an octet for the other one by a double bond. But then how about these? Well, these guys can make, this octet can be made up from each one of the nitrogens. Okay. So we could move 2 of those over here like that. So you got an octet there, and just do the same thing all the way around with nitrogens. So that's where it gets confusing. You know, where do you put the extra electrons? Then if we put the pair here, it can go there. Now we have an octet for everybody. Now that's the way you solve it with what we know, what we understand, and what we've trained for. If you know the name, tetracyanoethylene. This is the cyano group. And this is ethylene. So tetracyanoethylene solves that problem easily, quickly. Except you won't get into that till organic chemistry, if you're headed that way. If you don't go that way, then you won't have access to that problem solution. This is the only way you can solve it with what we know. Okay. Let's move on to the ones that are highlighted. Number 9. Oops, we lost Madison. Internet probably went up. Pi bond is the result of. Okay, how do we get a pi bond? We have 2 atoms. Let's just, for convenience, let's just say they're 2 carbons. If we have these 2 carbons attached to one another, and say they're attached to something else like that. Or why don't we make it 2 like that? So if these are hydrogens, trying to use a real example, then we should have, let's see, 2, 4, 6, 8, 10. And we have 8, 9, 10, 11, 12. That means we have 2 more left over. Right? So to make an octet, those 2 go over here. Now that's the way we would approach it from a VSEPR stand. Do the Lewis structure, then we know that this is trigonal planar. But the question is, how does that pi bond form? At this point, we're still talking about hybridization. So with this, what type of hybridization does this carbon exhibit? It's an sp2, right? An sp2. That gives us a sigma, sigma, sigma. That pi forms from the extra p that's unused on each one, and those p's overlap to give you that pi bond. And one of them is a sigma. On axis is the sigma. Off axis overlap is the pi bond. So which one of these fits best? It's not an overlap of s's or an s's and p's. C says overlap of 2 p orbitals along their axis. That can't happen, right? Because they're parallel to each other and separated by 2 atoms. So it has to be a sideways overlap. D's looks pretty promising. Overlap of 2 parallel p orbitals. And sideways overlap of 2 s orbitals doesn't happen because s orbitals are spherical. So they don't have to go sideways. Doesn't do them any good anyway. So D is the best answer. It's a sideways overlap of p orbitals. In the valence bond theory, right? We're still working with that at this point. How about 10? Okay. With these 3 molecules, which molecules have particles that share an electron pair to create a pi bond? Oh, there's Brooklyn. Okay. So when do you overlap p orbitals to get a pi bond? Whenever you see a double or triple bond, you've had a sideways overlap of p orbitals. Now, how many of these have that? Right? If you see one of these between atoms, single bond, that's sigma. If you see one of those, that means you've got at least 1 pi. So every one of them, all of them have p orbitals that share electrons to create a pi bond. Right? The first one has 3 of them. Second one has 2, and the last one only has 1. But they all have pi bonds. And whenever you see a double bond, one of them has to be a pi. You can only have 1 sigma bond between 2 atoms. Oh, we're going to work on that same set of structures. Now, what's the question? Which molecules have equivalent carbon-carbon bonds throughout the molecule? All right, this is a little more difficult. All right, so we have, let me put them in the same place they do. Here, here, here. And then the second one is here, and here, right? And the third one is it over here? Yep. Okay, those are all real molecules. But which ones have all equivalent carbon-to-carbon bonds? In organic chemistry, these are carbons. All right, wherever these two lines meet is a carbon. So we have 6 carbons in each molecule. But those carbons don't have octets unless you also adhere to another organic chemistry convention, which is each carbon has 4 bonds. And if you don't show anything bound to the carbon, it's a hydrogen. So this has to be a hydrogen. This is a hydrogen. There's a hydrogen. Like that. So each one of those has an octet. This one has 1 hydrogen here, 1 here, 1 here. This one has 2. Make an octet. And this one has 2. This one has 2 here, 2 there, 2 there, 2 there, and 1 here and 1 here. Okay. So this goes back to the very last part of the chapter discussion, where we talked about delocalized electrons. When you have an alternating double and single bonds, you have the opportunity to delocalize electrons over all of those. This one doesn't do it. It's only got 1. When you have a double, single, double, you can delocalize. When you have a double, single, double, single, double, single in this structure, the whole thing overlaps. And that gives you exactly the same equivalent bonds throughout the molecule. This one, these bonds right here, these 3 would be equivalent, but these 3 would be different. Okay. This is benzene. It's the classic example of delocalized electron structure. And when you delocalize electrons, you stabilize the molecule. The more you can delocalize, the better. And that's why these are, benzene is an aromatic. Now, there's more to the story than just the name, but aromatics are all extremely stable structures, and they're always cyclic. In the natural world, from my background in soil science, when you take a plant, it dies and you bury it in the ground, the first things that are attacked by microorganisms are the side groups. They chop those off like nobody's business. Then they go after the straight chains. Then they go after the cyclic ones, but the cyclics that are not aromatic. In other words, they don't have the delocalized. They're easier to attack. The last ones to go, and sometimes they don't go for a long time, I'm talking about thousands of years, are the aromatics. So we get, most of the aromatics we get are from oil, well, and coal, buried fossil fuels. They've been buried in the ground so long, there's nothing left but simple carbon compounds and aromatics. Okay, so the simple answer is I is the correct answer for that one. All right. Let's see, 12. The electron configuration of a particular diatomic species is, and this is the shorthand version. Now we're into molecular orbitals. So we have a sigma with a 2s, and it has 2 electrons. Then we have a sigma star from the 2s with 2 electrons. Then we have a sigma 2p with four electrons. No, two, sorry. This is sigma. It can only have two. Sorry. A pi 2p can have four electrons because there are two of them. And then a pi star 2p, a pi star 2p, it only has two electrons in it. So this one would be like that, like that, like that. And this one would be like that. Just if you're curious. And each one of these would be like that. Okay. What's the bond order for the species? It's a simple calculation. Remember, the bond order is simply the bonding electrons, right? 2, 4, 8. Minus the non-bonding, the anti-bonding. 2 and 2 is 4, right? 4 divided by 2. So that's 4 divided by 2 is 2. Correct? Did I do that right? That should be 12. 2, 4, 6, 8, 12. Yeah. So the bond order should be 2. D. And this shorthand version is derived from that longer version, that energy diagram where I showed the atom, and then the molecule in the middle where they come together. This is just the shorthand version. We could construct that energy diagram from this shorthand. It'd be very simple. We wouldn't necessarily know where the orbitals came from because it doesn't tell us what the molecule is. It just tells us what its molecular structure is. 13. As the bond order of a bond increases, the bond energy does what? Well, look at our choices. We got first blank is increase, decrease, second blank is increase, decrease. Okay, so when the bond order increases, what happens to the bond energy? Remember what we mean by bond energy. How much energy do you have to put into the molecule to break the bond? So the bond energy increases as the bond order increases. If we go from bond order 1 to 2 to 3, then the bond order also increases. The second one, so that means A or C would be a good candidate. The bond length does what? It shrinks, right? As you increase the strength of the bond, it draws those atoms closer together. So the bond length decreases. So increase, decrease is C. And we don't need more information. We have all we need to know right there. And the bond order is roughly equivalent to single, double, triple. Only with bond order, you can have fractions. All right, 15. Doing good. How many unpaired electrons in F2 2+ ion are based on molecular orbital theory, the order of the molecular orbital? So it gives you the molecular orbital order so that you can populate them in the correct energy order. So let's say we're working on F2 2+, which means it should have, let's see, we're working from we're leaving out the core electrons. So we only want valence electrons. That would be 14 minus 2 would be 12 electrons. So let's see, we have sigma pi, okay, sigma 2s, sigma star 2s, sigma 2 pi. No. Yeah, 2p, that's right. And then pi 2p, and then pi star 2p, and then sigma star 2p. So there's no SP mixing for this one. And that stands to reason. Fluorine, oxygen and fluorine don't exhibit SP mixing. Nitrogen to the left, XP mixing, which means these two would be reversed. Pi would come first and sigma would come second. But for this one, that's the proper order. And we have 1, 2, 3. We have 2 here, 1 there. Okay, so we can put them in. 2, 2 here, 2 here, 2, 4, 6. We got 6 more. 2, 1, 2, 3, 4. Okay, got that one. And then we have 2 more, right? 1, 2. But 2, 4, 6, 8, 10, 12. These would be unpaired because of Hund's rule. Okay, so the order of the molecular, let's see, how many unpaired electrons? There are 2 unpaired electrons. Now, would this one be diamagnetic or paramagnetic? Remember the difference? Paramagnetic means it's attracted to a magnetic field. Dia means it's opposed to. Para, the Greek prefix para means alongside or with. So that makes more sense. It likes a magnetic field. Dia means opposed to the magnetic field. So this would be paramagnetic. It has 2 unpaired electrons. All it needs is 1, but 2 would make it paramagnetic and actually stronger than 1 with only 1. You can measure the difference between the 2. Okay, so the answer is C. All right. Moving on. To number 19. The hybridization of the central atom in ClF2+. Okay, so we're going backwards now. ClF2+. Yeah. Okay. So we start off with 3 halogens. 3 times 7 is 21 electrons. But we've got a positive charge, which means we've lost one of those electrons. There are only 20 electrons in that structure. Okay. Now, which one goes in the middle? Well, the one is below and to the left of the other one. Either way, chlorine is below and to the left of fluorine, or it's below fluorine. So chlorine would go in the middle, and then fluorines would go out here like that. So that's minus 4 with 16 electrons. Okay. 2, 4, 6, 8, 10, 12. We got 4 electrons left over. Fluorines are full. We have to put those 2 here and here. And of course, it has positive charge. Now the question is, hybridization on the central atom. Well, the central atom has 1, 2, 3, 4 groups, which means tetrahedral. And tetrahedral is sp3. Okay, that's why the answer is C. Okay, 19. And 21. Which of the following does not contain at least 1 pi bond? Okay. All right. E says none of the above. I think we can discount that one because I see carbon dioxide in there. We know it has pi bonds. So A, B, C, and D, we just look at those. The ones that we've drawn already in the past, I'm going to go ahead and just throw those in. And we'll do the other ones longhand. CO2, we know this one is. That's got pi bonds. Let's see. C2H4 and C2H6, right? Okay. So how about this one? We've got 2 electrons here, got 4 there and 6 there. So that's 12 electrons. We have a carbon, we have an oxygen, and we have 2 hydrogens. It's 2, 4, 6. We've got 6 electrons left over. Okay. 2, 4, 6. We don't need to put them over here because they're already filled, right? Hydrogen only needs to do that. So how do we make an octet out of carbon? We just take one of those pairs and do that. That has pi bond. Okay. How about this one? Let's see. 2 times 4 is 8, and 4 times 4 is 4 times 1 is 4. So that's 12 electrons. 2 carbons, 4 hydrogens. 2, 4, 6, 8, 10. 12. We need to make an octet for one of those, for those carbons, like that. That's got a pi. Okay. So this one has, this one also has 8, but it has 6 here. So that's 14. Carbon, carbon, and 3 hydrogens each. Okay. 2, 4, 6, 8, 10, 12, 14. That's it. So this one has no pi bond. There's your answer. B. Okay. This is ethylene, and this is ethane. And carbon dioxide, and this is formaldehyde. Right. Everybody smelled. Taking a, have you ever dissected a fetal pig? No, they preserve them with formaldehyde. You open the bag and it hits you in the face. You never forget the smell. I say fetal pig because I don't do cats. They wanted me to teach anatomy and physiology again and dissect a cat. I say, no, thank you. Cats are pets. They're not cadavers. 24. Complete the Lewis structure for the following molecule. Okay, it gives you part of it. It doesn't finish it for us. And then it asks you how many sigma and how many pi bonds are in this molecule. Okay, so here we go again. This carbon, this CH3, has the hydrogens attached to that carbon. And that carbon is attached to the next carbon with that hydrogen separated. And this is called a methyl group. The hydrogens are like that. That's what you need to understand when you see a molecule drawn like that. This is an organic compound. And the convention is when you write it straight like that, simplified, those hydrogens are attached to that carbon, and this one is attached to the next one. So we have another carbon over here with an oxygen, and we have another carbon with a nitrogen, right? Is that 4 carbons? 1, 2, 3, 4, plus this one, 5, then an oxygen, then, okay. So now we're going to finish the Lewis structure. We have 1, 2, 3, 4, 5, 6, 7. 7 hydrogens, so that's 7 electrons. We have 1, 2, 3, 4, 5 carbons. 5 times 4 is 20. And we have 1 oxygen, is 6, and 1 nitrogen, which is 5. So 13, 38, right? Is that correct? 6, yeah, 38 electrons. Okay, we've already established connections for 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26. 12 electrons. Work from outside in. These hydrogens already have what they need, and those carbons already have their octets. So we're working on this side over here. 12 electrons. 2, 4, 6, 8, 10, 12. There we go. Now we got all of our electrons placed. How do we make? Well, these electrons are going to be assigned to that carbon. These electrons are going to work with this carbon because they're not going to jump carbons. So in order to get an octet here, we have to form like that. In order to get an octet here, all we need is that. Okay. So now, how many sigma bonds? Any place you've got two atoms bound together, there's a sigma. You have to have a sigma before you can have anything else. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigmas. And then the double bonds or triples. So we have a pi here, we have a pi there, and we have a pi there. So there are 3 pi's. Okay, 13 and 3. That would be E. Okay. All righty. Now we're down to 26. Consider this skeleton. NCCN. Okay. Draw the Lewis structure and answer the following. All right, here again, they're telling us to draw the Lewis structure for that. So we have to assume that there are no other atoms in there, not even hydrogens. So 2 times 4 is 8. And 2 times 5 is 10, right? Yeah. So that's 18 electrons. So we're going to go 2, 4, 6. Those have already been used up. That means we have 12 electrons. 2, 4, 6, 8, 10, 12. Okay. Now, the simplest way to make this work is to put electrons over here on this side of the carbons. Just leave this one single bond here, that's sigma, and add up here to make the octets. That would be like that, and like this, like that. Okay. So how many pi bonds does the molecule contain? 1, 2, 3, 4. 4 pi bonds. That also is C. All right. And 27. Which of the following molecules contains the shortest carbon-carbon bond? All right. A, B, C, D. E says B and D are the same. Well, let's see about that. C2H2, C2H4, we just drew that one. And C2H6, we just drew that one. And C2Cl4. And then this is B and D. All right, we're looking for the shortest carbon-carbon bond. This one we drew just a second ago. This is ethane. That's a single bond, a sigma bond. This one is ethylene. Remember? It had a double bond here. It has sigma and a pi. This one's shorter than that one. This is, let's see, we have drawn this one before. I need to work it out. We can do that. That's 8 plus 2 is 10. Carbon, carbon, hydrogen, hydrogen. 2, 4, 6. So we need 4 more. 2, 4. 1 here, 1 there. That's acetylene. Or ethine, whichever. They both work. This one has a sigma in the middle has a pi here and a pi here. This is the strongest carbon-carbon bond, the shortest and the strongest, because it has a sigma and two pi's. This one only has a sigma and a pi. This is a sigma. This one would be like that one. So we would draw it like this, like that, and like that. Now it would be, it's not this one. B and D look similar, but well, we found our answer. A is the answer to the problem. But if we compare B and D, it looks like they have the same. They have a sigma and a pi. The problem is chlorine is very electronegative, more electronegative than hydrogen. So it's going to draw electron density away from that bond and weaken the bond. So B is stronger than D. Okay, in case anybody wonders or asks you. 28. Doing good on time, I think. Well, we're going to have oodles of time on Tuesday because we don't have a lab. See the weather. When comparing Be2 and H2, beryllium and molecular hydrogen. So what are we looking at? Be2 is more stable because it contains both bonding. H2 has a higher bond order. H2 is more stable. H2 is more stable. Okay. So I think we need to look at the structures. Right? Hydrogen is going to be like this. That's it. It only has 2 electrons. Beryllium has 4 electrons, 4 valence electrons. So beryllium is going to be like that with 4 electrons. And then just like that. Right? That gives us 4 electrons. But there's no way we can get an octet out of that. It's deficient. All right. Okay. So they're both linear. Let's look at each one of these. Roman numerals 1, 2, 3, and 4. Number 1 says Be2 is more stable because it contains both bonding and anti-bonding valence electrons. Okay. They're looking for, this one has a sigma 1s and a sigma star 1s. Both of those electrons are there. Beryllium has sigma 1s, sigma star 1s, sigma 2s, and sigma star 2s. Okay, these are both full. Well, I didn't count them up here. We still have 2 here and 2 here. Maybe we better do that. Let's count up everything. So it's be 8, right? 8 electrons total. So we have 2, 4. We need 4 more. 2, 4. Okay. Yeah. It's unlikely that this molecule even exists. Right? What's its bond order? It's 4 minus 4 divided by 2. 0 divided by 2 is 0. This has a bond order of 0. This has a bond order of 1. Right? 2 divided by 2 is 1. All right. So 1 says beryllium is more stable. No, it's not. If its bond order is 0, it's definitely not more stable. Roman numeral 2. All right. So this one's out. H2 has a higher bond order than Be2. That's true. Definitely. H2 is more stable because it only contains sigma 1s electrons. Okay. Yeah, it has no anti-bonding electrons. I'll buy that. Then 4, H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. Neither one is right. They would both be diamagnetic, right? Because this is a full orbital, full. They'd both be diamagnetic if this one existed, which is unlikely. So it's only 2 and 3, which is C. Okay. All right, moving on. To number 29. Which of the following species is paramagnetic? Okay. A, B, C, D, A, B, C. They're both homonuclear diatomics. That's good. So A. Let's see, do I want to string them out down or across? Yeah, we'll string them out down. All right, C2 and O2F2, O2F2, and Li2. All right. So this one, I think the best way to approach this one is to use the useful information I give you in the back. C2 has sigma, sigma star, and pi, 2p. Sigma, sigma star, and pi. This is 2p. This is, yeah, 2s and 2s. We leave out the cores. So what do we have? Well, we have 2, 4, 8. We have 8 here. 8 electrons. 2, 4, 5, 6, 7, 8. Okay, and that agrees with the diagram. Yes, this one is diamagnetic. We're looking for paramagnetic, right? This is diamagnetic. O2 would do like this. So 1 and 2. So this one has a sigma from 2s, sigma, I need to put these down a little further now. A sigma star from 2s, a sigma from 2p, and a pi from 2p. Because there's no mixing here. We would have put the S from 2p on this side because there's mixing. Right, carbon, nitrogen to the left is mixing, oxygen and fluorine are not mixing. So the sigma would come first. All right, and since we're only dealing with valence here, we've got 12 valence, right? Yeah, 12. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, and then the next one is pi star 2p, because sigma star is out here. Right, and then we have 2 more. So this one is paramagnetic. Oxygen is paramagnetic. Fluorine has 14. So, and it follows the same pattern as oxygen. So it's 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. This one is diamagnetic. There are no unpaired electrons with that. Lithium. Lithium is like, let's see. Well, lithium, we're only dealing with 2 valence electrons. So actually, we're only looking at this right here. Just like that. Lithium is diamagnetic. So the only one that's paramagnetic is oxygen. Yeah. Let's see. We have lithium in this one. Yeah, there's lithium. No, it's not. It tells us the order of orbitals, but it doesn't populate. That's okay. We just did. Okay. And remember, these, I'm leaving out the cores, right? The cores are all full, so they don't matter. But the valence tells us what we want to know. Oxygen's the only one that's paramagnetic. The rest repel from a magnetic field. Right, let's see, 30. Okay, we got 15 minutes. See how many more I got. 30. 2, 3, 4. I didn't mark those. Okay, yeah, we won't have any trouble finishing on Tuesday. Oops, one more. Well, 30. Here we go. All right. For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? All right, B2, C2, P2, and F2. B2, C2, P2, and F2. Okay, so again, to save yourself some time, I'd go to the given here. Sigma, sigma star, and pi. This is sigma, sigma star, and boron, yes, pi, P, and sigma, P. Let's go ahead and add some more. And this would be pi star. This would be sigma star. Okay. Then we can work our way down. For this one, and that one, but not this one. So we'll have to do this one separate. So boron has 3, 6, 2, 4, 5, 6. Does that look right? Yeah, it agrees with the. Okay, so we don't need those for that one. Carbon is also sp mixing, but carbon has 8, 2, 4, 5, 6, 7, 8. So carbon, this one is, what's the question? Bond order. Okay, we're going to do the bond order in just a minute. We got to get these structures first. Phosphorus is like nitrogen. All right, I'm going to have to do it this way. Nitrogen works from the third level. 3s, sigma star, 3s, I, 3p, sigma, 3p, And phosphorus is going to be like nitrogen, 10 electrons. 2, 4, 5, 6, 7, 8, 9, 10. Because phosphorus is in the third period. And then fluorine is back up in the second period. So I guess I'll have to draw it again. But it goes like this. And with no mixing. Actually, it doesn't matter. If we're only calculating the bond order, it really doesn't matter. Phosphorus has 14. Okay. So 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. You don't need this one. And now we can do the bond order. Okay. Bond order equals. All right, we have 1, 2, 3, 4. 4 minus 2 divided by 2. Right? So that's 1. Carbon is 2, 4, 5, 6 minus 2 divided by 2 equals 1.5, right? Let's see. This is 2, 4, 6, 8 minus 2 divided by 2 is 2. Oop, no, it's not. 3. 8 minus 2 is 6. There we go. And let's see, this one is 2, 4, 6, 8 minus 2, 4, 6 divided by 2. So that's equal to 1. Okay, back to the question. Following, does the bond order decrease if you add 1 electron? Okay, where are we going to add electrons? This is neutral. I'd look at it this way. If you want to decrease the bond order, you increase the anti-bonding electrons. So when we add an electron, the ones where the electron goes into anti-bonding will decrease it. Right? If we put one here, nope. If we put one here, nope. If we put one here, yep, that'll decrease to 2.5. And if we put one here, we're out to 5 star. Well, that will decrease also. And make it 1/2. All right, so 2 of them will experience a decrease in bond order if we add an electron. All right. That's a lot of work for just one little question. But it is true nonetheless. What are we doing on time? Have time for one more. Just like to just smear it up. Order the following from shortest to longest bond. Don't forget the effect of atomic radius and orbital size. Okay. I'm going to try this one. Let's see, shortest to longest bond. All right, I'll tell you what. In the interest of time, let's do this thing. C2B2H2, C2B2H2, and N2. from shortest to longest bond. So the strongest to the weakest bond. And we might want to consider orbital size also. Okay. So, dicarbon. All right, if we're gonna, let's calculate bond order first. So if we look at our thing here, we've got 2, 4, 6 bonding minus 2 anti-bonding. Okay. So that's 1.5. Diboron, we have 2, 4 minus 2 divided by 2, which is bond order 1. Hydrogen, well, we have a bond order of 1. We've done that so many times. Bond order of 1. And nitrogen has a bond order of 3 because it is 2, 4, 6, 8 minus 2 divided by 2. It's 3. Okay. So if we just order them, if we put them in order by these numbers from shortest to longest, strongest to weakest. So strongest would be nitrogen at 3. And then the next would be the dicarbon at 1.5. And then we have a tie, apparently, between diboron and hydrogen. Okay. Since these are bond orders of 1, which one gets the nuclei closest to one another? Hydrogen is working with a sigma 1s. Right? It's got a sigma 1s with 2 electrons. Diboron is working with a sigma. Yeah, is working with a sigma 2s. And a sigma star 2s and a pi 2p to get here. What happens is you're overlapping, they have the same bond order, but you're overlapping closer nuclei. So you're getting them closer to each other. That means that it should be reversed. In other words, we should have hydrogen here and boron there. So it should be NCHB. Oh, wait a minute. Order the following shortest to, shortest to longest. I'm sorry. Boron should be left where it is. But nitrogen is also a large nucleus. So the dihydrogen is going to be closer. Even though it's only a bond order of 1, the nuclei are going to be closer. The bond length is going to be shorter. Because you can't get the nuclei close enough together when you're talking about 7 protons and 7 neutrons in that nucleus, and you're overlapping second period orbitals. Here you're only overlapping first period. Right, so this one actually would go over there. That's the trick to this one. So HNCB would be the best answer. Okay, that's probably all we can get done today.